Hi, and welcome to the second lesson in the rates of reaction topic. This one's going to look at how we can use practical investigations to measure the rate of different reactions. So we're going to start by introducing you to the three methods that we could do this with. So the first method that we've got is this one here, and this is measuring the decrease in mass of a reaction mixture. Now, the first method and this second method both require you to pick a reaction that will produce a gas. And what will happen is in the first one, this one here, you will measure how much gas is lost, and so the mass goes down over time. And in the second one, this one right here, you would actually collect the gas that's produced and then work out how much is produced over the time period. Our final one is this method right here, measuring the decrease in light passing through a solution. This method actually would allow us to see how a solution changes as a solid is produced. And so what would happen is the reactant would produce a solid, that solid precipitate would block the light going through, and then over time we would work out how fast that reaction is actually happening at. Okay, so let's start with our first practical, and that's measuring the decrease in mass of a reaction mixture. So what we would do is we take a top pan balance like this one right here. We would place our reaction vessel on top of it, and then we would mix our reactants like the marble chips and hydrochloric acid into the reaction vessel. We would then take a start mass at the very beginning, and then after that we would time a set amount of time and take readings. So for example, we might say every 30 seconds we will write down what the mass then is. This will give us this shaped graph. So what we can see is the graph actually goes down and then it will plateau right here. And that plateau is because the reaction has actually finished happening. It has lost the maximum that it will lose, and so it can't react anymore. One thing you guys need to remember, in a question that comes up quite a lot in an exam, is why do we put a cotton wool bung in? So this actually allows the gas to escape, but at the same time stops anything else getting in. So that actually preserves the experiment. It stops anything getting into the reaction mixture that might cause it to change or to produce a different kind of reaction, and allows the thing that we're trying to measure to actually escape and give us a set of results. Okay, guys, so the second method is this one right here. And in this one, again, we're measuring gas, but this time we're actually collecting the gas. And there are two ways we can do this. We can do this with this piece of equipment right here, which is called a gas syringe. So what will happen is you will put your reaction mixture in your vessel, and you will have a delivery tube coming out of the bung in the vessel and leading to a gas syringe like this. As the gas is produced by this reaction mixture, it will pass up through here and it will push the syringe out. So what you would do then is, say every 30 seconds, you would read where it's sitting on the syringe and you would record that volume of gas. Now we can actually do this another way, and what we can do is we can get a dish and we can fill that dish with water, and then we can get an upturned measuring cylinder like so, also filled with water. And then what that would allow us to do, just colour that in, so imagine that's all the water there. What that allows us to do is, if we fed our delivery tube in here like that, as the bubbles of gas come through from our reaction mixture, it would displace the water, and eventually what we would get is we would get a bubble of gas here like that at the top, and that would also then give us a volume of gas produced over time. Our final method that we can use is this one right here, and this is measuring the decrease of light passing through a solution. This one needs our solution to produce a solid product, and that solid product will be the precipitate that blocks the light. A good example of this that comes up quite often in exams is the reaction between sodium thiosulfate and hydrochloric acid. And so what you would do is you would draw a cross on a piece of paper and you would sit your reaction vessel on the cross. You would put one of your reactants in the vessel and then you would add the other one starting a timer and giving it a swirl. And what you're going to do is you're going to look straight down your vessel like that. And then what you're looking for is for the moment at which you can no longer see your cross. The light isn't passing through it anymore, and so you would stop the timer and write down the time it took to do that. You can use this to test how concentration or how temperature would affect the reaction by either repeating it multiple times with different concentrations of solution or repeating it multiple times with different temperatures for the solutions. And again, just like we've seen previously, our graph would be this downwards curve. Our graph at this point would end at some point as well, because it's going to stop the reaction completely, and that's the point at which you wouldn't be able to see it anymore. Okay, guys, so as part of this and using practical results, we also need to do some maths in chemistry. And one of the first things in chemistry that I'm going to talk to you about in terms of maths is calculating your surface area to volume ratio. Okay, so there are 3 steps to actually do this. Your first step is to find your surface area. Your second step is to find your volume, and then your third step is to find your surface area to volume ratio. Okay, so if we are looking at our cube here, to find our surface area, we are going to do 3 times 3 times 6. So our 3's come from here, the 3 on the side here and the 3 on the bottom there, and our 6 comes from the number of faces for our cube. Okay, guys, so if I put that into a calculator, which I'm going to do right now while I am sitting here, our value for our surface area for this one would be 54 centimeters squared. Then we would do our volume, and for volume we're going to do 3 times 3 times 3. This one here, this one here, and this one here. So if I do that in my calculator, I would get 27 centimeters cubed. Okay, so how do we work out surface area to volume ratio? Well, what we're going to do is we are going to divide the surface area by the volume. So what we will be doing here is we will be doing 54 divided by 27, which should give us, if I am correct in my maths, an answer of 2. And that will give us a 2-to-1 ratio. Okay, guys, so what that means is the surface area is twice the size of the volume. Okay, so you guys need to be able to do that in the exam. This is actually a skill that's transferable between chemistry and biology, because for some of your biology questions, you may be asked to calculate the surface area of a cell or the surface area to volume ratio of a cell, so you can work out whether or not a surface and its transfers works. Okay, guys, so the second set of calculations that I'm going to have to show you today are using a tangent to find the gradient. Now, this is only relevant if you are sitting the higher paper. So if you aren't sitting higher paper, guys, skip past this in the video because you don't need to know that. So most of our reactions that we look at in chemistry for this topic are reactions that give us a curve of best fit. And it makes it more difficult to work out the reaction rate on a curve because we can't plot from the line. So what we do instead is we draw a tangent, and that tangent is basically a straight line that touches the point on a curve, or a given point on a curve. So an example of this would be, your exam board would say something like, find the rate of reaction at 50 seconds. And so you would draw your tangent so that it touches the line just here where 50 seconds is. And then you use that straight line to draw a right angle triangle. This would be our right angle triangle here. And then what we will find, guys, is we would find the change in y and the change in x. And then we would work out the rate. So in this case, our rate would be 0.7 divided by 100. And if I do that in my calculator, that would give me 0.007. And then we have to put together our units. Our units are going to be grams per second, because it's grams divided by seconds, and that's how we find our rate for a given point. Now, we might also be asked to find the rate for the time at 0. Now, we would do that by actually drawing our straight line so that it hits our curve at 0 and goes up like that. I know that's not the best line, but I was drawing it freehand. Obviously, you guys would use a ruler to do this. Remember to make sure that you try to get your line on those to just touch the point at 0 and nothing else, and then use it to work that out. What you should find with that is at 0, it should be the fastest rate. And it should be the fastest rate because it has the highest concentration of reactants. And what that means is you have lots of reactants which will be colliding together. They will be reacting more because there are more collisions. As the reactant level goes down because the reaction has gone on, the rate will drop because there are less reactive particles out there colliding and breaking their bonds. Okay, guys, so that is the end of this video. If you need to, please watch it again, go through the steps. I would suggest that everyone makes a note of how to do this, who's doing tired here, because this is a common question that comes up, and it's an easy skill to get 3 to 4 marks on in an exam. Those 3 to 4 marks for you guys would be nice, easy pickups in your exams. I'll see you again very soon in another video about this.